Beyond the orbit of Neptune, there is a graveyard the size of a solar system, and it is still growing. Trillions of frozen bodies drift there in near total darkness, untouched since before the sun had finished forming. Some of them are mountains of ice, tumbling silently through the void. Others are worlds larger than entire countries, hiding in a region so vast and so dim that we did not even confirm its existence until the final decade of the 20th century. This is why the outer edge of our solar system is not the calm, empty border we once imagined it to be. It is a chaotic, restless, and genuinely unsettling place, filled with objects that periodically break loose and come screaming back toward the inner planets, carrying secrets about how our entire solar system was built and how it might one day be unbuilt. Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath and let's begin. For most of human history, we believed the solar system ended at Neptune. Beyond that final blue giant, we assumed there was simply nothing, an infinite black hallway leading toward the stars. We were wrong in almost the most dramatic way possible. Starting in the early 1990s, astronomers began finding faint points of light drifting far beyond Neptune, moving too slowly to be comets and too small to be planets. At first, there were just a handful, then dozens, then hundreds. Today, we know of many thousands of these objects, and models suggest the true number of bodies larger than 100 kilometers across could reach into the hundreds of thousands, with countless millions of smaller fragments filling the gaps between them. This region has a name now, the Kuiper Belt, named after the astronomer Gerard Kuiper, who theorized decades before the discovery that such a structure might exist. Ironically, Kuiper himself did not think it would survive to the present day. He believed that if such a disk of icy debris had formed alongside the planets, it would have been swept away or ejected long ago. He was wrong, and the region he doubted would exist turned out to be one of the most important structures in the entire solar system. The Kuiper Belt begins around the orbit of Neptune and stretches out to roughly 50 times the distance between Earth and the Sun, an almost incomprehensible ring of debris that dwarfs the more familiar asteroid belt between Mars and Jupiter, both in size and in sheer population. If the asteroid belt is a scattering of rubble left over from a failed planet, the Kuiper Belt is something else entirely. It is a frozen time capsule from the earliest days of the solar system, made of material that never fully assembled into anything larger, preserved in a deep freeze so complete that some of its objects have not meaningfully changed in 4.5 billion years. And within that ancient debris field lies almost everything we still do not understand about how our solar system came to look the way it does. The Kuiper Belt is not a uniform ring, and this is where things start to get strange. Astronomers who study it divide the region into distinct populations, each with its own orbital behavior, its own history, and its own mysteries. The first group is called the classical Kuiper Belt objects, sometimes nicknamed cubewanos after the first object of this type ever found. These bodies travel on nearly circular orbits, gently inclined, moving in a calm and orderly procession around the Sun. They are considered the most primitive population in the entire solar system, largely undisturbed since the era of planetary formation. Some of them are almost shockingly white and reflective, coated in exotic ices of methane and nitrogen that have never been warmed enough to darken or evaporate away. Then there are the resonant objects, bodies locked into precise mathematical relationships with Neptune's orbit. Pluto itself belongs to this group, completing 2 orbits around the Sun for every 3 orbits Neptune makes, a rhythm so stable that despite their paths crossing on paper, Pluto and Neptune can never actually collide, This resonance protects Pluto the way a perfectly timed dance protects two partners from ever stepping on each other's feet, no matter how close their paths appear to come. Thousands of other objects share this same 3-2 rhythm with Neptune, and astronomers have found entire families locked into other resonances as well. Some circling the Sun once for every 2 orbits of Neptune, others tracing out far more intricate ratios. These gravitational relationships did not happen by accident. They are fossils of a violent and dynamic period billions of years ago, when Neptune itself was migrating outward through the solar system, sweeping objects into these resonant traps like a slow-moving net, gathering everything in its path. Beyond the classical and resonant populations lies something far less orderly, a chaotic population called the scattered disk. These objects have been gravitationally kicked by Neptune onto highly elongated, steeply tilted orbits that can carry them from just beyond Neptune's path out to distances hundreds of times farther from the Sun than Earth. Eris, one of the largest and most massive bodies ever found beyond Neptune, belongs to this scattered population, and its existence was part of what forced astronomers to reconsider the very definition of a planet. The scattered disk is not calm. It is a region of near misses, unstable paths, and objects whose futures cannot be predicted with certainty even a few million years out, let alone across the full lifetime of the solar system. Some of these bodies will eventually be flung into the outer darkness entirely, lost from the Sun's gravitational grip forever. Others will be nudged inward, beginning a slow, chaotic fall toward the inner solar system that can end many millions of years later, as a bright comet streaking across our night sky. There is a fourth category, too, and it may be the strangest of all. A small handful of objects called detached objects or sednoids, named after the dwarf planet Sedna. These bodies orbit so far from the Sun and on paths so extreme that Neptune's gravity can no longer meaningfully influence them at all. Sedna itself swings from a closest approach, still farther than Pluto ever travels, out to a distance so extreme that a single orbit takes more than 10,000 years to complete. Nothing we currently understand about the solar system's formation fully explains why Sedna's orbit looks the way it does. Some models suggest a passing star billions of years ago tugged it onto this strange path. Others propose something even stranger, still waits undiscovered in the darkness, an idea we will return to later, because it may be the most unsettling mystery in this entire region of space. Scattered throughout these populations are worlds that defy the simple image of the Kuiper belt as nothing but rubble and ice chips. Pluto is the most famous of these worlds, and for good reason. Despite losing its status as the 9th planet in 2006, Pluto remains a genuinely complex and active place, not the frozen, dead rock many people still imagine. Its surface is a patchwork of nitrogen, ice plains, water ice, mountains taller than anything in the Alps, and dark reddish material scientists believe forms when sunlight and cosmic rays break apart simple molecules into more complex organic compounds. Pluto even appears to have a thin, hazy atmosphere that partially collapses and refreezes onto the surface as its long, elliptical orbit carries it farther from the Sun, then rises again as it swings back closer. It takes Pluto roughly 248 years to complete a single circuit around the Sun, meaning it has not yet finished even one full orbit since its discovery in 1930. Orbiting Pluto is Charon, a moon so large relative to its parent world that the two bodies do not simply orbit one another in the usual sense. Instead, they orbit a shared point in space that lies outside Pluto itself, making the pair something closer to a double world than a planet and its satellite. Beyond Pluto and Charon, 4 smaller moons complete the system. tumbling in orbits so chaotic that some of them appear to flip end over end unpredictably, a phenomenon almost never observed anywhere else in the solar system. Then there is Eris, discovered in 2005, and for a time believed to be even more massive than Pluto itself. Eris orbits so far from the Sun, on such a steeply tilted and elongated path, that its surface temperature drops low enough for its thin atmosphere to freeze completely onto the ground during the coldest stretch of its multi-century orbit. The discovery of Eris was not a minor footnote in astronomy. It was the single event that triggered the International Astronomical Union to formally define what a planet actually is, a definition that ultimately excluded both Eris and Pluto from that category, and created the new classification of dwarf planet in its place. Haumea is stranger still, a world spinning so fast that it has been stretched into an elongated, almost football-shaped body, completing a full rotation in only about 4 hours, one of the fastest rotation periods of any known object of its size in the entire solar system. That extreme spin likely came from a colossal impact deep in the past, an impact so violent it also created a ring system around Haumea and scattered several icy moons, and even a family of smaller fragment objects that still share Haumea's orbital neighborhood. Today, all bearing the same telltale signature of pure water ice on their surfaces. Makemake, named after a creation deity of the Rapa Nui people of Easter Island, is nearly as bright and reflective as Pluto, coated in frozen methane that gives it a distinctly reddish hue. For years, Makemake appeared to be one of the only large trans-Neptunian objects without a known moon, until a faint, dark companion was finally detected orbiting it. A moon so much darker than Makemake itself that it seems to be made of an entirely different kind of material, raising new questions about how such contrasting bodies could have formed together. And then there is Arakoth, a name that means sky in the Powhatan and Algonquian language, the most distant object ever visited by a spacecraft, and perhaps the most pristine, untouched relic of the early solar system that humanity has ever directly observed. Arakoth looks like two flattened lobes gently fused together, the shape of a snowman lying on its side, and its structure reveals that it formed through an extraordinarily gentle collision. Two separate bodies drifting together so slowly that they simply merged rather than shattering. This tells scientists something profound, that the early solar system, at least in this remote region, was calmer and more orderly than the violent, high-speed collisions we imagine dominating the era of planet formation elsewhere. Each of these worlds, Pluto, Eris, Haumea, Makemake, and Arakoth, represents only the largest and brightest examples astronomers have found so far. Current models suggest the Kuiper belt could be hiding dozens more objects of dwarf planet size that we simply have not detected yet, scattered across a region so vast, so distant, and so dim that even our most powerful telescopes struggle to pick them out from the surrounding darkness. Reaching any of these worlds is one of the most difficult challenges ever attempted in space exploration. The New Horizons spacecraft launched in 2006, and it needed nearly a decade of travel at speeds faster than any human-made object before it, just to reach Pluto. When it finally arrived in 2015, it became the first and only spacecraft to closely observe Pluto, revealing a world so much more geologically active and visually stunning than anyone expected. Mission scientists had quietly worried Pluto might turn out to be a featureless, ancient, crater-covered ball of ice, a relic that had not changed in billions of years. Instead, they found young, crater-free plains of nitrogen ice slowly convecting like a lava lamp. Mountain ranges made of frozen water harder than rock at Pluto's temperatures, and evidence that liquid water might still exist deep beneath the surface. kept from freezing solid by the friction of Pluto and Charon's gravitational relationship, and by heat from radioactive decay in Pluto's rocky core. But New Horizons was not finished. After its flyby of Pluto, mission controllers redirected the spacecraft deeper into the Kuiper belt, toward a small, distant object that would later be named Arrokoth. On the first day of January, in the year 2019, New Horizons flew past Arrokoth at a distance far closer than its earlier pass by Pluto, capturing the most detailed images ever taken of any object in this region. This flyby remains, and will likely remain for a very long time, the most distant close encounter with any world in the history of human spaceflight. The data it sent back, traveling for hours across the solar system, even moving at the speed of light, confirmed that the Kuiper belt truly is a museum of frozen history, holding physical evidence of conditions from the first few million years after the solar system's birth. To understand why this region has remained so pristine, you have to understand just how extreme its environment really is. At the distance of the classical Kuiper belt, sunlight arrives so weak and so diffuse that the sun itself would appear as barely more than an unusually bright star in the sky, offering almost no warmth at all. Surface temperatures across most of this region hover only a small number of degrees above absolute zero, cold enough that gases we consider permanent on Earth, like nitrogen, methane, and carbon monoxide, exist there as solid ice, sometimes even forming glaciers that flow with agonizing slowness across the surface of these distant worlds. There is no meaningful atmosphere to speak of on most Kuiper belt objects, no wind, no weather, in any sense we would recognize, just a silent, airless vacuum interrupted occasionally by the faint hiss of solar wind particles striking bare ice. Darkness defines this region as much as cold does. From Pluto's surface, the sun provides roughly 1,000 times less light than it does here on Earth, and the farther out you travel through the scattered disk and beyond, that already faint light continues to fade toward nothing. Many objects in the outer reaches of the Kuiper belt receive so little sunlight that they exist in something close to permanent, starlit gloom, illuminated mainly by the combined dim glow of the surrounding stars, rather than by any warmth from their own distant sun. It is a place built for stillness, for waiting, for preservation, a natural freezer vast enough to hold the memory of the solar system's birth intact for billions of years, largely undisturbed by the light, heat, and chaos that define the inner planets. And yet, despite this stillness, the Kuiper belt is anything but static. Beneath its calm, frozen surface lies a region of constant, low-level gravitational conflict, one that has been quietly reshaping orbits, ejecting objects, and sending icy wanderers plunging toward the sun for billions of years, and continues to do so today. Many of the comets that streak across our night sky did not begin their journey in some distant, poetic corner of infinite space. They began right here, in the Kuiper belt, as quiet, frozen bodies indistinguishable from millions of their neighbors, until a chance gravitational nudge from Neptune sent them tumbling inward. Short-period comets, the ones that return to our skies again and again on predictable schedules measured in years or decades rather than millennia, mostly trace their origin to this region. Halley's Comet is the most famous exception, technically belonging to a slightly different dynamical family, but comets like Encke and countless fainter ones, catalogued only by number, are true Kuiper belt refugees. Icy fragments slowly leaking out of the outer solar system and falling toward the sun. The process usually begins subtly. An object in the scattered disk drifts just close enough to Neptune's gravity for a small orbital nudge, and that nudge compounds over thousands of years, gradually reshaping a nearly stable orbit into something wilder and more elongated. Eventually, The object crosses into the realm of the giant planets, where Jupiter, Saturn, Uranus, and Neptune each take turns tugging at its path, flinging it further inward or sometimes back outward again, in a chaotic gravitational relay race that can last millions of years before the object finally settles into a shorter, more predictable orbit closer to the Sun. By the time we see one of these objects as a comet, streaking across the sky with a glowing tail stretching millions of kilometers behind it, we are witnessing the final act of a journey that began in total darkness billions of years earlier in a region of space most people have never even heard of. The tail itself is proof of just how untouched these bodies were before their fall. As a Kuiper belt object approaches the Sun and begins to warm for the first time in billions of years, its surface ices do not melt in the way ice melts on Earth. Instead, they sublimate, transforming directly from solid ice into gas, releasing trapped dust and debris that has been locked inside since the birth of the solar system. This is why studying comets gives scientists a way to sample the ancient Kuiper belt without ever sending a spacecraft that far. Because every comet is essentially a small, delivered piece of that distant, frozen archive, carried inward by gravity and unlocked by sunlight for the first time. Not every ejected Kuiper belt object becomes a beautiful comet, however. Some are thrown in the opposite direction entirely, flung outward by a close encounter with Neptune or one of the other giants, eventually leaving the solar system's gravitational influence altogether. Others are pushed only partway, ending up in the vast, sparsely populated region between the Kuiper belt and the far more distant Oort cloud, an intermediate zone where a slowly growing population of exiled bodies drifts in near total isolation. Over the roughly 4.5 billion year history of the solar system, this constant, quiet leakage has likely removed a significant fraction of the Kuiper belt's original population, meaning the belt we observe today, vast as it still is, may be only a fragment of what it once contained in the earliest era of planetary formation. There is one mystery buried inside the Kuiper belt that continues to unsettle even experienced planetary scientists, and it involves something we still have not directly seen. For over a decade, astronomers have noticed a strange pattern among the most extreme objects in the outer solar system. The detached bodies like Sedna and a handful of others with similarly stretched, distant orbits. Instead of pointing in random directions, as basic physics would predict for objects perturbed by nothing but the ordinary planets we already know about, these extreme orbits appear to cluster together, their closest approaches to the Sun all aligned in roughly the same direction, their orbital planes tilted in oddly similar ways. Random chance alone struggles to explain this kind of alignment. When researchers ran the numbers, they found that the probability of this clustering happening purely by coincidence was small enough to take seriously as a red flag, a signal that something else might be quietly shaping these orbits from the shadows. The leading explanation proposed by some astronomers is the existence of an undiscovered ninth planet, sometimes called Planet 9, a world potentially several times the mass of Earth, orbiting the Sun at a distance so extreme that a single orbit could take somewhere between 10,000 and 20,000 years to complete. If it exists, this hypothetical planet would be far too distant and far too dim for our current telescopes to easily detect through direct imaging, hiding in the same vast darkness that swallows so much of the outer Kuiper belt. Its gravity, however, would be more than strong enough to gently herd smaller, distant objects into the aligned, clustered orbits astronomers have already observed. Acting like an invisible shepherd standing at the edge of a field, keeping its flock loosely gathered without ever needing to reveal itself directly. This is precisely what makes the idea both compelling and deeply unsettling. We are not talking about a small asteroid or an overlooked comet. If Planet 9 is real, it would be a genuine major planet, several times more massive than Earth, sitting quietly at the edge of our own solar system, unseen by every telescope pointed skyward for the entirety of recorded human history. Not every scientist accepts this explanation. Some argue that the clustering could be a statistical illusion caused by the limitations of our current survey techniques, since the same regions of sky are far easier to search than others, potentially biasing which extreme objects we happen to find in the first place. Others propose that the clustering might instead be explained by the combined gravitational influence of a large number of small, undiscovered Kuiper belt objects acting together, rather than requiring a single, massive, hidden planet. A few researchers have gone even further, suggesting the observed effects might not point toward a planet at all, but towards something stranger still, a small, ancient, primordial black hole no larger than a grapefruit, quietly orbiting far beyond Neptune, its gravity betraying its presence even though it emits no light of its own. This idea sounds almost too strange to take seriously, yet it emerged from legitimate calculations because a captured primordial black hole of the right mass could theoretically produce a very similar gravitational signature to a full-sized undiscovered planet, while remaining almost impossible to detect through any method other than the subtle way it nudges the objects around it. Searches for Planet 9 continue using some of the most powerful telescopes and surveys ever built, scanning enormous swaths of sky for the faint, slow-moving point of light that a genuine ninth planet would produce as it crept along its multi-thousand-year orbit. So far, nothing conclusive has been found. This means one of two things is true. Either the hypothesis is wrong, and some subtler bias in our data collection is creating a pattern that does not actually exist, or there really is a massive, undiscovered world quietly orbiting our sun right now, invisible to every eye and every instrument humanity has ever built, patiently completing an orbit so long that it has not finished a single circuit since before the pyramids were constructed. Either answer would reshape how we understand the true architecture of our own solar system. To understand why the Kuiper belt looks the way it does today, scattered, resonant, chaotic in places and eerily calm in others, scientists had to look back to the very earliest years of the solar system, a period of dramatic rearrangement that shaped everything we now observe. The leading framework for this early chaos is often called the Nice model, named after the city in France where it was developed, and it describes a solar system that did not form quietly in its current configuration, but instead underwent a violent, large-scale reshuffling not long after the planets first solidified. According to this model, Jupiter, Saturn, Uranus, and Neptune did not originally form in the positions we see them occupying today. Instead, they formed much closer together, embedded within a much larger disk of icy debris that once extended far beyond where the Kuiper belt sits now. Slow gravitational interactions between the giant planets and this surrounding disk gradually caused Jupiter to migrate slightly inward, while Saturn, Uranus, and Neptune were pushed steadily outward. At some point, Jupiter and Saturn's orbits may have crossed a critical resonance, a moment when their gravitational influence on one another suddenly intensified, triggering a period of dramatic instability throughout the entire outer solar system. Uranus and Neptune were flung outward on wild, eccentric paths, plowing directly through the ancient disk of icy material that once surrounded them. This upheaval scattered countless objects in every direction. Some were ejected from the solar system entirely, lost forever to interstellar space. Others were flung inward toward the inner planets, an event some scientists connect to the Late Heavy Bombardment, a period roughly 4 billion years ago when the Moon, and likely Earth as well, appear to have been struck by an unusually intense wave of impacts. Still others were captured into the stable, resonant orbits with Neptune that we still observe today. A direct fossil record of exactly where Neptune happened to be and how quickly it was moving during this ancient and violent migration. The classical Kuiper belt objects, the calm, nearly circular population, likely represent material that was simply left behind after Neptune's outward migration settled down, undisturbed survivors from the outer edge of the original disk. The scattered disk, by contrast, represents the debris that was violently kicked during the chaos itself, objects still carrying the scars of that ancient instability in the shape of their wild, unpredictable orbits today. This origin story explains something that puzzled early Kuiper belt researchers for years: why the region contains so much less mass than early models predicted it should. Calculations based on how planets are believed to form suggested the original disk beyond Neptune should have contained enough material to build several more Earth-sized worlds. Instead, the current Kuiper belt contains only a small fraction of that expected mass, a discrepancy explained almost entirely by this ancient period of ejection and scattering, when the vast majority of the primordial material was thrown away, inward or outward, leaving only a diminished remnant population behind. In other words, the Kuiper belt we study today is not simply a leftover. It is a survivor, the remaining fraction of a much larger structure that was violently reshaped in the solar system's early chaos. Its current shape, a direct fingerprint of exactly how that ancient reshuffling unfolded. There is a more immediate and practical reason the Kuiper belt deserves our attention, one that has nothing to do with ancient history and everything to do with the future. We track near-Earth asteroids with reasonable confidence, cataloging the vast majority of objects large enough to cause serious damage if they ever crossed our planet's path. The Kuiper belt is an entirely different story. Because these objects are so distant, so dim, and so numerous, our current survey capability has only mapped a small fraction of what almost certainly exists out there. We have confidently identified only a few thousand Kuiper belt objects directly, yet models based on the objects we can see suggest the true population of bodies larger than 100 kilometers across, likely numbers in the hundreds of thousands, with the population of smaller, but still potentially dangerous, objects reaching into the millions. Most of these bodies will never come anywhere near Earth. Their orbits remain safely locked far beyond Neptune for the remainder of the solar system's existence. But the scattered disk population is, by definition, unstable, and every year, a small number of these icy wanderers get gravitationally nudged onto paths that carry them steadily inward, crossing the orbits of Uranus, then Saturn, then Jupiter, on a journey that can take millions of years to fully play out. We generally have enormous advance warning for objects this large, often centuries or millennia, because their orbits, once detected, can be traced and refined with high precision. The genuine unease comes from a subtler problem, the sheer scale of what remains completely undetected. An object several hundred kilometers across, similar in scale to some of the mid-sized bodies already known in the Kuiper belt, could in principle exist on an unstable, slowly evolving path without our current survey techniques having found it yet, simply because it is too distant, too dark, and too faint for existing telescopes to reliably catch, especially if its orbit rarely brings it into the more thoroughly searched regions of sky. This is not a prediction of imminent danger. It is instead an honest admission of how much of our own solar system remains functionally invisible to us, even in the modern era of space telescopes and automated sky surveys. Every large object we do eventually find in the Kuiper belt tends to arrive as a surprise, discovered not through some systematic completion of a known catalog, but through the slow, patient process of scanning small patches of an enormous, dark sky and hoping something moves against the background stars. New and more powerful observatories are gradually closing this gap. Wide-field surveys, capable of repeatedly imaging enormous swaths of sky, are expected to substantially increase the known population of trans-Neptunian objects over the coming years, potentially resolving long-standing questions about clustering, hidden planets, and the true total mass of the entire region. Until then, the honest scientific position is a strange kind of humility, an acknowledgement that the outer boundary of our own home solar system remains less thoroughly mapped than the surface of many of the very Kuiper belt worlds we have already visited up close. People frequently confuse the Kuiper belt with the true edge of the solar system, but these are not the same boundary at all. And understanding the difference reveals just how layered our cosmic neighborhood really is. The sun constantly sheds a stream of charged particles called the solar wind, which inflates a vast protective bubble around the entire solar system, known as the heliosphere. This bubble extends well beyond the Kuiper belt, out to a boundary called the heliopause, the point where the pressure of the outward flowing solar wind is finally overwhelmed by the pressure of the interstellar medium, the thin gas and charged particles that fill the space between stars. Voyager 1 crossed this boundary in 2012, becoming the first human-made object to leave the heliosphere and enter true interstellar space, even though it had already passed through the outer Kuiper belt region years earlier. In other words, leaving the Kuiper belt behind does not mean leaving the sun's influence behind, and crossing the heliopause does not mean reaching the true gravitational edge of the solar system either. That true gravitational edge lies much farther out still, in a distant, spherical shell of icy bodies called the Oort cloud, a structure so far away that its inner boundary begins roughly where the detached objects like Sedna orbit, and its outer edge may extend nearly a full light-year from the sun, almost a quarter of the distance to the nearest other star. The Oort cloud is believed to be the true source of long-period comets, the rare visitors that swing through the inner solar system only once every few thousand or even few million years, arriving from seemingly random directions rather than the flattened plane where the planets in the Kuiper belt reside. Unlike the Kuiper belt, which lies roughly in the same flat plane as the planets, the Oort cloud is thought to form a vast, roughly spherical shell surrounding the entire solar system, a final, enormous halo of debris marking the outermost limit of the sun's gravitational dominance before interstellar space truly begins. No spacecraft has ever come close to reaching the Oort cloud, and at current spacecraft speeds, it would take tens of thousands of years just to arrive at its inner edge. This layered structure, planets, then the Kuiper belt, then the heliopause, then finally the distant Oort cloud, means the Kuiper belt functions almost like a doorway rather than a wall, a transition zone between the orderly, planet-dominated inner solar system and the much larger, more chaotic, and far less understood outer reaches beyond it. And occasionally, something arrives through that doorway from the opposite direction entirely. In 2017, astronomers detected an object moving through the solar system on a hyperbolic trajectory, a path so extreme it could only mean the object had arrived from beyond our solar system altogether and was simply passing through before continuing on its way back into interstellar space forever. Named Oumuamua, this strange, elongated visitor became the first confirmed interstellar object ever observed, followed 2 years later by a second confirmed visitor, an active comet named Borisov, and more recently by additional detections as our survey capabilities have improved. These interstellar wanderers pass directly through the same region occupied by the Kuiper belt on their way in and out, briefly mingling with our own solar system's ancient debris before continuing their own multi-million-year journey between the stars. It is a humbling reminder that the boundary of our solar system is not sealed shut. Material moves both ways, and the same icy region that quietly stores the remnants of our own solar system's birth is also, occasionally, a crossroads for travelers from entirely different star systems altogether, carrying with them a physical sample of chemistry formed around a sun that is not our own. The Kuiper belt is not a strange anomaly unique to our own solar system either. When astronomers point powerful telescopes at nearby young stars, they frequently detect faint rings of dust and debris encircling them at distances comparable to where our own Kuiper belt sits. Structures astronomers now call debris disks, and which many consider to be Kuiper belts, in the process of formation around entirely different suns. One of the most striking examples surrounds a star called Fomalhaut, a bright, youthful star not too different in mass from our own sun, encircled by a strikingly narrow, sharply defined ring of debris. The narrowness and sharpness of that ring puzzled astronomers for years, until models suggested it could be shaped by the gravity of an unseen planet, shepherding the debris into its narrow band, the same way Neptune's gravity has shaped the resonant structure of our own Kuiper belt. Other systems show debris disks warped, tilted, or gapped in ways that similarly hint at unseen planets sculpting them from within, planets too faint and too deeply buried in surrounding dust to be directly imaged, but whose gravitational fingerprints are unmistakable in the shape of the debris around them. These observations matter enormously for how we understand our own solar system's history. They suggest that the process which built our own Kuiper belt, planetary migration, gravitational sculpting, violent early instability, and a long, slow settling into calmer, resonant order, is not some rare, unique event. It appears to be a common, perhaps even standard, part of how planetary systems form and mature across the galaxy. Every star, with a substantial debris disk, may be hosting its own version of the chaotic reshuffling described by the Nice model, its own scattered disk of unstable, icy fragments, and quite possibly its own hidden Planet 9 equivalent, quietly shepherding the outermost material into alignment. This gives the Kuiper belt a strange kind of cosmic significance far beyond our own solar system. It is not simply the outer attic of our own home, cluttered with old, forgotten material. It is also a local, close-up example of a nearly universal process, one astronomers can study in exquisite, close-range detail here, and then use as a template for interpreting far dimmer, far more distant debris disks glimpsed only as faint smudges of dust around other stars, many light-years away. In a sense, every time we learn something new about our own Kuiper belt, whether from a spacecraft flyby, a subtle gravitational clustering pattern, or a newly discovered icy dwarf planet, we are also learning something about the billions of other planetary systems scattered throughout our galaxy, most of which we will never be able to visit or observe in anywhere near this level of detail. One of the more unexpected discoveries about the Kuiper belt is just how common binary systems are within it. On Earth, we think of moons as a rare exception, one planet, one companion, in most cases. In the Kuiper belt, this pattern is reversed. A significant fraction of the objects astronomers have studied closely turn out to be binaries, two roughly similar-sized bodies locked in a mutual orbit, sometimes so close together that they nearly touch, and sometimes separated by distances that would seem impossibly wide for such small, low-mass worlds to remain gravitationally bound. Arrokoth itself, before New Horizons revealed it to be a single fused object, was suspected to be exactly this kind of loosely orbiting binary pair, and its ultimate shape, two lobes gently joined together, shows that the line between a binary system and a single contact object can be remarkably thin, separated only by how gently or how violently two bodies happen to come together. This abundance of binaries offers another clue about the ancient, gentle conditions that once prevailed in the outer solar system. Binary objects like these are fragile. A single, violent collision, even a relatively minor one by cosmic standards, would likely destroy such a delicately balanced system, sending the two components tumbling apart or smashing them together entirely. The fact that so many binary Kuiper belt objects have survived intact for over 4 billion years suggests this region has remained remarkably free of destructive, high-speed collisions since its earliest history. A peaceful graveyard rather than a violent battlefield, at least on the small scale of individual objects colliding with one another. The colors and surface compositions of Kuiper belt objects add another layer of mystery. Some are a deep, startling red, colored by complex organic molecules called tholins, formed when simple ices like methane are bombarded for billions of years by cosmic rays and ultraviolet light, gradually building up longer, more complex, reddish-brown molecular chains on the surface. Others are almost pure white, coated in fresh, highly reflective ices of nitrogen or methane that have not yet been chemically altered by this same long-term radiation exposure. Still others appear distinctly grayish or neutral in tone, hinting at surfaces dominated by water ice mixed with darker, carbon-rich material. This color diversity is not random. Astronomers have found that it correlates with orbital characteristics, suggesting that objects formed in different original locations within the primordial disk, at different temperatures and with access to different raw ices, ended up with distinctly different surface chemistry. Chemistry that has remained essentially frozen in place ever since, because there has been no significant heat source strong enough to melt, mix, or reset it in the billions of years since these worlds first formed. In this sense, every Kuiper belt object functions as an individual chemical time capsule, and their differing colors are not simply an aesthetic curiosity, but a genuine scientific record, an ancient chemical map of exactly what conditions were like across different regions of the young solar system's outer reaches, preserved in a way that nothing in the warmer inner solar system, disturbed constantly by heat, weathering, and geological activity, could ever hope to match. Perhaps the most quietly astonishing possibility raised by our exploration of this region is that some of these frozen, distant worlds might not be entirely frozen at all. When New Horizons studied Pluto's surface in detail, scientists noticed features that were difficult to explain without invoking liquid water at some point in the relatively recent geological past. A massive basin called Sputnik Planitia, filled with slowly convecting nitrogen ice, shows almost no impact craters at all, meaning its surface has been resurfaced repeatedly, likely by material welling up from below, in a process that requires some source of internal heat far greater than sunlight alone could provide at Pluto's extreme distance. That heat likely comes from the slow, steady decay of radioactive elements buried within Pluto's rocky core. The same basic process that keeps Earth's own interior warm, just operating here at a much smaller scale, in a much colder world. Combined with the insulating effect of a thick layer of ice above it, this internal heat may be enough to maintain a layer of liquid water, likely mixed with ammonia or other antifreeze compounds, in a hidden ocean sandwiched between Pluto's icy shell and its rocky interior. If this is correct, Pluto may be quietly hiding more liquid water beneath its surface than exists in all of Earth's oceans combined. An almost unbelievable idea for a world sitting in a region so cold that nitrogen itself freezes solid. Pluto is not necessarily unique in this regard. Similar internal heating processes, combined with insulating icy shells, are suspected on several of the icy moons orbiting the outer gas giants, worlds like Europa and Enceladus, both strongly suspected to harbor subsurface oceans of their own, kept liquid by a combination of radioactive decay and tidal flexing from their host planet's gravity. The Kuiper Belt's largest dwarf planets may share this same hidden potential, quietly maintaining liquid water reservoirs far from any star's warmth, kept in a delicate thermal balance between the cold of deep space above and the gentle, persistent heat rising from within. This possibility carries genuine significance for the search for life beyond Earth. Everywhere we have found stable liquid water on our own planet, we have also found life, thriving even in the most extreme environments imaginable, from scalding deep-sea vents to permanently dark caves sealed off from sunlight for millions of years. If liquid water genuinely persists within Pluto, or within other large Kuiper Belt worlds like Eris or Haumea, then these frozen, distant bodies, sitting in a region so cold and so dim that direct sunlight barely qualifies as warmth, might theoretically host the basic chemical conditions necessary for life, entirely independent of any nearby star's energy at all. We have no direct evidence that life exists in any of these hidden oceans, and the challenges facing any organism there would be immense. No sunlight for energy, extreme pressure, and a chemical environment we still understand only poorly. But the mere possibility that a warm, liquid, potentially habitable environment could exist this far from the sun, hidden beneath a shell of ice in one of the coldest, darkest regions of our entire solar system, is enough to keep planetary scientists returning to this distant region again and again, hungry for more data, more flybys, and more missions capable of studying these worlds up close. Exploring the Kuiper Belt is unlike almost any other exploration challenge humanity has ever attempted, and the sheer scale of the distances involved explains why so few missions have ever ventured there. New Horizons, the fastest spacecraft ever launched directly from Earth, still needed nearly a decade of travel time just to reach Pluto, and that speed advantage came from a very specific and unrepeatable launch trajectory that used the gravity of Jupiter itself as an additional slingshot boost, even traveling at speeds that would be almost unimaginable in any everyday context. New Horizons still could not simply stop or turn around once it reached Pluto. Slowing down enough to enter orbit around a distant world requires carrying enormous amounts of propellant, weight that would have made the entire mission impossibly heavy and expensive to launch in the first place. Instead, missions like New Horizons are essentially one-shot flybys, racing past their target in a matter of hours after a journey lasting years, gathering as much data as physically possible in that brief window before continuing onward, forever, into the depths of the outer solar system with no way to return. This is why, even after New Horizons, we still have only ever seen close-up detail from two Kuiper Belt objects, Pluto and Arrokoth, out of a population that likely includes hundreds of thousands of significant bodies. Every other object in this vast region remains known to us only as a faint point of light, its color, size, and orbit, inferred indirectly through careful, painstaking measurements taken from telescopes stationed here on Earth or in orbit around it, rather than through any direct, close-range observation. Sending a dedicated orbiter, a spacecraft capable of slowing down and remaining in orbit around a Kuiper Belt object rather than simply flying past it, would require propulsion technology, significantly more advanced than what currently exists, along with a power source capable of operating reliably for over a decade in a region so far from the sun that traditional solar panels become essentially useless. Most deep space missions to this region instead rely on small nuclear generators, converting the natural decay heat of radioactive material into a slow, steady trickle of electricity, a technology that itself is becoming increasingly scarce and expensive to produce. Despite these enormous challenges, scientists continue proposing new missions to this region, some envisioning a dedicated orbiter for Pluto and Charon, others proposing missions to Eris, Haumea, or other large dwarf planets that New Horizons never had the opportunity to visit. None of these proposed missions have yet moved beyond the conceptual and early planning stages, largely due to the enormous cost, the multi-decade timelines involved, and the intense competition for space agency funding from missions targeting closer, faster, and cheaper destinations. This means that for the foreseeable future, our understanding of the vast majority of the Kuiper belt will continue to come primarily from distant, indirect observation rather than direct exploration, a genuinely humbling reality, given how much of our own solar system this region actually represents. We have walked on the moon. We have driven rovers across the surface of Mars. We have landed probes on comets and asteroids, yet the largest, most populous region of our own solar system by physical volume remains almost entirely unexplored, visited directly by a single spacecraft, twice in the entire history of human civilization. The debate over Pluto's planetary status, which still occasionally flares up in public conversation even now, was never really about Pluto at all. It was about the Kuiper belt itself, and what its discovery meant for how we define a planet in the first place. When Pluto was first found in 1930, astronomers had no idea it belonged to an enormous surrounding population of similar icy worlds. It was treated as a solitary oddity, a small, distant planet that simply did not fit neatly alongside the gas giants or the rocky worlds of the inner solar system, but a planet nonetheless, because there was nothing else nearby to compare it to. That assumption held for over 60 years, until the discovery of the broader Kuiper belt in the early 1990s revealed that Pluto was not alone at all. It was simply the first, and for a long time the largest known member of an entire population of similar worlds. As more and more Kuiper belt objects were found throughout the following decade, some scientists began to argue that if Pluto counted as a planet, then dozens, and eventually potentially hundreds, of other newly discovered Kuiper belt objects should logically count as planets too. The situation reached a breaking point with the discovery of Eris in 2005, an object initially believed to be more massive than Pluto itself. If Pluto was a planet, astronomers reasoned, then Eris almost certainly had to be considered one as well, and the solar system might soon need to accommodate not 9 planets, but a rapidly expanding, potentially unlimited number, as survey telescopes continued finding more and more large trans-Neptunian worlds. This forced the International Astronomical Union to finally establish a formal, precise definition of what a planet actually is, a definition adopted in 2006 that required a planet to orbit the Sun, to have enough mass for its own gravity to pull it into a roughly round shape, and crucially, to have gravitationally cleared its orbital neighborhood of other significant debris. Pluto satisfies the first 2 conditions easily, but fails the third, because it shares its orbital region with an enormous surrounding population of Kuiper belt objects, some of which cross its own path entirely, rather than having swept that region clear the way the 8 recognized planets have each done within their own orbits. This decision remains genuinely controversial among some planetary scientists, not because anyone disputes the underlying facts about Pluto's environment, but because many argue the formal definition, based partly on orbital neighborhood clearing, describes an object's surroundings rather than any intrinsic physical property of the object itself, and creates strange edge cases depending on how far a planet happens to sit from its star. Regardless of where individual scientists land on this ongoing debate, the reclassification accomplished something genuinely important. It forced the entire scientific community, and by extension the general public, to reckon with the true scale and population of the Kuiper belt for the very first time. Pluto did not become less interesting or less worthy of study the moment it was reclassified as a dwarf planet. If anything, its demotion drew far more attention to the extraordinary population of worlds surrounding it. Worlds that had gone largely unnoticed by the public for over a decade after their initial discovery, quietly accumulating in number while most people continued imagining a solar system that ended cleanly at Neptune. The tools we use to hunt for these distant worlds have improved dramatically since the first Kuiper belt discoveries in the early 1990s. Yet the fundamental challenge remains staggering. A typical Kuiper belt object reflects only a tiny fraction of the already faint sunlight that reaches it at such extreme distances, meaning even large objects appear as nothing more than an extremely dim point of light, easily lost among the background glow of far more distant stars and galaxies. To find one, astronomers typically photograph the same patch of sky multiple times over the course of several nights, then compare the images, looking for anything that appears to have shifted position slightly against the fixed backdrop of distant stars. Anything that moves is a candidate, a possible object within our own solar system rather than a star or galaxy light years away. And each candidate then requires additional observation over weeks, months, or even years to confirm its orbit, with enough precision to be certain it is real and to understand what kind of object it actually is. This is painstaking, methodical work, closer to searching for a single grain of sand shifting position on a beach, photographed from a great distance, than to the dramatic, instant discoveries often portrayed in popular imagination. A new generation of survey telescopes is poised to transform this search dramatically. Facilities capable of repeatedly imaging enormous areas of sky with exceptional sensitivity are expected to increase the total known population of trans-Neptunian objects by a significant multiple over the coming years, potentially finding tens of thousands of new Kuiper belt objects that have simply never been bright enough, or fallen within a previously searched patch of sky for older instruments to detect. This new wave of discovery carries the potential to finally resolve some of the Kuiper belt's most persistent mysteries. If a genuine ninth planet exists, shepherding the observed clustering of extreme, detached orbits, a sufficiently thorough survey should eventually catch its faint, slowly moving signature, even at a distance where its light is stretched thin across an enormous span of sky. If the clustering instead turns out to be a statistical illusion caused by uneven search coverage, a truly comprehensive survey covering the entire sky with consistent depth should reveal that as well, by finally showing extreme orbits distributed randomly rather than suspiciously aligned. Either outcome would represent genuine scientific progress, closing one of the more persistent open questions in modern planetary science, a question that has lingered specifically because our past searches, however impressive for their time, never covered enough of the sky, deeply enough to give a truly complete picture of what actually orbits out there. Until that more complete picture arrives, every new Kuiper belt discovery continues to function almost like a message in a bottle. A single data point pulled from an ocean of darkness so vast that even our best current estimates of its total population carry enormous uncertainty, sometimes varying by a factor of 10 or more, depending on which model astronomers choose to trust. We are, in a very real sense, still taking the first steps toward genuinely mapping our own solar system's largest structural feature, more than 3 decades after we first confirmed it exists at all. The chaos that shaped the Kuiper belt billions of years ago has never fully stopped. It has only slowed down, and that distinction matters more than it might first appear. Neptune continues to gravitationally interact with objects at the inner edge of the scattered disk today, exactly as it did during the ancient instability, just at a far gentler and slower pace than during those first chaotic hundreds of millions of years. Computer models that simulate the orbits of scattered disk objects forward in time reveal a genuinely unsettling property. Many of these orbits are what scientists call chaotic in the mathematical sense, meaning their future paths cannot be reliably predicted beyond a certain point, because even an infinitesimally small uncertainty in an object's current position compounds over time into a completely different possible future. An object that appears stable for the next million years in one simulation might appear to be ejected entirely from the solar system in another simulation that started with only a microscopically different initial position, a property that makes long-term forecasting for many scattered disk objects genuinely impossible, not merely difficult. This means the population of the scattered disk is not simply drifting towards some final, settled equilibrium. It is instead engaged in an extremely slow, ongoing process of attrition, continuously losing objects to ejection, to inward comet-producing falls, and occasionally to direct collisions, while very rarely gaining new members pulled loose from the more stable classical belt through subtler, longer-term gravitational effects. Some of the objects ejected during this ongoing process do not simply drift away gently. They can be flung outward with enough velocity to escape the sun's gravity entirely, becoming what astronomers call rogue objects, unbound wanderers that continue drifting silently through interstellar space forever, no longer orbiting any star at all. Based on how common this ejection process appears to be within our own solar system's history, and by extension, within the countless other planetary systems believed to have undergone similar early instabilities, astronomers now suspect that free-floating, unbound, icy, and rocky objects, essentially former Kuiper belt equivalents cast out from their home systems, may actually outnumber the stars in our entire galaxy, drifting silently between star systems in numbers that could reach into the trillions. This means that somewhere in the darkness between here and the nearest stars, there are almost certainly countless former Kuiper belt objects, both from our own solar system and from others, tumbling endlessly through the void with no sun to orbit and no light to reflect, essentially invisible unless one happens to drift close enough to a star or to a waiting telescope for us to notice its passage. The interstellar visitors we have already detected, Oumuamua and Borisov, among them, may represent only the barest handful of objects from this vastly larger, silent population, one that vastly outnumbers every star we can see in the night sky combined, yet remains almost entirely undetectable except in the rarest of circumstances. It is a strange thought to sit with, that the quiet, icy debris field at the edge of our own solar system is not simply a local curiosity, but a small, still active piece of a much larger, galaxy-spanning process, one that has been quietly scattering material between the stars for as long as planetary systems themselves have existed. The small moons orbiting Pluto and Charon deserve their own closer look because they behave in ways that violate almost every intuition we have about how moons are supposed to move. Beyond the massive, mutually orbiting pair of Pluto and Charon, 4 much smaller moons complete the system, named Styx, Nix, Kerberos, and Hydra, each only a few tens of kilometers across, tiny, irregularly shaped fragments likely created from the same ancient, gigantic collision that formed Charon itself billions of years ago. Because Pluto and Charon orbit a shared point in space rather than one simply circling the other, the gravitational environment experienced by these smaller, outer moons is fundamentally different from anything a moon orbiting a single, stationary planet would encounter. Instead of feeling a steady, predictable gravitational pull from one central body, these small moons are constantly tugged back and forth by the combined, shifting gravity of both Pluto and Charon as the two larger bodies spin around their common point. Observations from New Horizons revealed that at least two of these small moons, Nix and Hydra, tumble chaotically as they orbit, their rotation axes flipping and rolling unpredictably rather than settling into the calm, steady spin most moons eventually lock into after billions of years of gravitational interaction with their parent planet. On Nix, this means there is no fixed north or south, no stable, predictable day-night cycle at all, just a slow, continuous, chaotic tumble that makes its rotation genuinely impossible to forecast beyond a certain point, in much the same mathematically unpredictable way that many scattered disk orbits are impossible to forecast far into the future. This chaotic tumbling is believed to result directly from the unusual, ever-shifting gravitational field created by the orbiting Pluto-Charon pair, a field that never settles into the kind of stable, symmetrical pattern that would allow a small moon's rotation to naturally damp down and stabilize the way our own moon's rotation did relative to Earth billions of years ago. It is a small, distant, almost overlooked detail buried within a much larger and more famous planetary system, yet it captures something essential about the Kuiper belt as a whole. A region where the ordinary, predictable rules governing motion in the inner solar system frequently break down entirely, replaced instead by genuine mathematical chaos, gravitational relationships so intricate and so sensitive to tiny changes that reliable long-term prediction becomes fundamentally impossible, no matter how powerful our computers eventually become. Haumea offers its own version of this same unpredictable complexity. Beyond its unusually fast rotation and elongated shape, Haumea possesses a thin, dark ring, the first ring ever discovered around any object beyond Neptune, along with two known moons named Hiyaka and Namaka, both likely fragments blasted free from Haumea's surface during the same ancient, violent impact that stretched Haumea itself into its current strange rugby ball shape. A scattered family of smaller icy fragments, all sharing remarkably similar orbital characteristics and near-identical surface chemistry, dominated by crystalline water ice, trails Haumea through space as well, the only confirmed collisional family currently known within the entire Kuiper belt. Direct physical evidence of a single, ancient, catastrophic event whose debris continues drifting together, loosely bound by little more than coincidence and shared history, billions of years after the original collision occurred. For decades, planetary scientists debated exactly how small icy bodies grow into larger ones during the earliest stages of solar system formation, a question that sounds simple but turned out to be surprisingly difficult to answer with confidence. One prominent theory, called hierarchical accretion, proposed that small particles gradually stuck together through repeated, often violent collisions, slowly building up larger bodies through a chaotic, high-energy process, resembling a demolition derby that somehow manages to build something instead of destroying it. A competing theory, called streaming instability or pebble accretion, proposed something gentler, that small pebble-sized particles could become concentrated by aerodynamic effects within the swirling gas and dust of the young solar system, clumping together under their own weak gravity, then merging with neighboring clumps at extremely low relative speeds, closer to a slow, gentle drift than any kind of violent collision. Arakoth became the single clearest piece of physical evidence supporting this gentler formation model. Its two lobes show no significant flattening, no cracking, no shattering. Nothing that would be expected from even a moderately fast collision between two solid bodies of that size. Instead, the way the two lobes align, their shapes, and their surface features all suggest they formed independently nearby one another, then drifted together so slowly, at a speed slower than a gentle walk, that they simply settled against one another and stuck, preserving both original shapes almost perfectly intact rather than deforming or cracking on impact. This single, distant, oddly shaped object, sitting in the coldest and darkest reaches of our solar system, effectively settled a scientific debate that had persisted for decades, providing direct physical proof that at least some planetesimals, the building blocks of planets, formed through this gentle, low-speed accumulation process, rather than through repeated, violent collisions. If small bodies throughout the early solar system formed this way, it suggests the process of building planets may have been calmer, quieter, and more orderly, at least in its initial stages, than the dramatic, high-energy imagery of colliding rocks and shattering debris that has long dominated both scientific illustrations and popular imagination. The violence came later, during the specific period of giant planet migration described by the NICE model, rather than being a constant, defining feature of the entire planet formation process from its very beginning. This distinction matters enormously for understanding not just our own solar system, but potentially thousands of other planetary systems throughout the galaxy, because it suggests that the gentle accumulation of small icy bodies into larger ones may be a nearly universal first step in building planets, one that occurs quietly and calmly before any larger-scale gravitational chaos, migration, or violent rearrangement has the chance to begin. Pluto experiences a seasonal cycle unlike anything found anywhere in the inner solar system. One stretched across nearly 2.5 centuries rather than a single year, and shaped as much by its unusually tilted, elongated orbit as by its distance from the Sun. Because Pluto's orbit is so eccentric, its distance from the Sun varies dramatically over the course of a single Plutonian year, swinging from its closest approach, just inside Neptune's orbit, out to a farthest point nearly twice as far away. This means the sunlight reaching Pluto's surface, already extremely faint even at its closest approach, becomes fainter still as it swings outward, triggering a seasonal cycle far more extreme than anything Earth experiences. As Pluto moves away from the Sun, temperatures across its surface drop low enough that its already thin nitrogen and methane atmosphere begins to freeze directly out of the sky, snowing gently down onto the surface as fresh ice, gradually thickening the very ice caps that will eventually sublimate again as Pluto swings back closer to the Sun many decades later. At its most extreme, models suggest Pluto's atmosphere may nearly vanish entirely during the coldest portion of its orbit, collapsing almost completely onto the surface before slowly returning as gas once the world begins warming again on its long, slow approach back toward the Sun. New horizons happen to arrive during a particularly favorable window in this long cycle, catching Pluto's atmosphere in a relatively active, gaseous state rather than during one of its more extreme collapsed phases, giving scientists a rare opportunity to directly observe atmospheric hazes, layers, and even evidence of methane ice clouds drifting through Pluto's thin, cold sky. This extended, extreme seasonal rhythm means that entire generations of any hypothetical observer stationed on Pluto would live through only a small fraction of a single full seasonal cycle, watching the same slow transition between a faintly hazy atmosphere and near total atmospheric collapse play out across a timescale that dwarfs any human lifetime many times over. It offers a striking reminder that even something as seemingly universal as the concept of a season looks radically different once you leave the narrow range of orbital conditions found among the four rocky inner planets, stretching into something almost unrecognizable once you reach the icy, eccentric orbits that define so much of the Kuiper belt. Modern planetary defense efforts have made real, measurable progress in recent decades, and it is worth being clear and fair about that progress before discussing where the remaining gaps lie. Space agencies around the world have cataloged the vast majority of near-Earth asteroids large enough to cause a genuinely global catastrophe, tracking their orbits with enough precision to confidently rule out any impact for at least the next century, and in most cases, for far longer than that. A mission called DART even demonstrated, for the first time in human history, that we possess the technical ability to physically alter the path of an asteroid, deliberately colliding a spacecraft with a small moon orbiting a larger asteroid and measurably changing its orbital period. Proof that deflection, given enough advance warning, is genuinely achievable. The genuine gap in our planetary defense capability lies specifically with objects originating from far beyond the main asteroid belt, long-period comets whose source lies in either the scattered disk or the far more distant Oort cloud. Unlike near-Earth asteroids, which follow relatively short, well-mapped orbits that bring them past Earth repeatedly, allowing decades or even centuries of advanced tracking, long-period comets from the outer solar system often make their first-ever approach toward the inner solar system entirely unannounced, discovered only months, sometimes only weeks, before their closest approach to the Sun and to Earth's orbital path. This is simply a consequence of where they come from. An object drifting quietly in the scattered disk, or the distant Oort cloud for billions of years, produces no detectable signature whatsoever until it begins actively venting gas as it warms near the Sun, meaning by the time we see it at all, it may already be uncomfortably close, with only a limited window remaining to plan any kind of meaningful response. The reassuring context here is genuinely important. Long-period comets capable of causing serious harm to Earth are believed to be extremely rare events on human timescales, arriving on average, perhaps once every many hundreds of thousands of years, based on the frequency of large impact craters found throughout Earth's geological record. The population of dangerous long-period comets is also simply much smaller than the population of near-Earth asteroids, because most of the material in the scattered disk and Oort cloud remains gravitationally locked in place for the entire multi-billion-year lifetime of the solar system, only rarely getting nudged onto a path that brings it anywhere near the inner planets at all. Even so, this remaining gap in advance warning time represents the honest, unresolved edge of humanity's current planetary defense capability, a limitation rooted directly in the vast distance, darkness, and sheer scale of the Kuiper belt and the regions beyond it, rather than in any lack of effort or technological ambition on our part. Closing that gap further will likely require exactly the kind of next-generation survey telescopes already being developed. Instruments capable of detecting faint, distant objects sooner, buying precious additional months or years of warning time for any future long-period comet that might eventually be found heading our way. A quiet, ongoing effort to extend our awareness a little further into the darkness with each passing decade. Not every surprise from the Kuiper belt requires a spacecraft flyby to uncover, and one of the strangest recent discoveries came from a modest-sized world named Quaoar, observed instead through a careful, ground-based technique called stellar occultation. Watching how Quaoar's shadow briefly dimmed the light of a distant background star as it passed directly in front of it. That observation revealed something that should not exist according to standard orbital theory. A thin, dense ring of material, circling Quaoar at a distance, more than twice as far out as the theoretical limit where rings are supposed to be able to survive. Every ring system we had previously studied, around Saturn, around Uranus, even the newly discovered ring around the small Centaur object Chariklo, existed well within what is known as the Roche limit, the distance from a body inside which tidal forces are strong enough to prevent loose material from clumping together into a moon, allowing a ring to persist instead. Beyond the Roche limit, conventional theory predicts that ring material should quickly clump together under its own gravity, forming a small moon within a relatively short span of time rather than remaining spread out as a ring indefinitely. Quaoar's ring exists comfortably outside this limit, and yet it persists anyway, a genuine puzzle that has forced scientists to reconsider whether some additional factor, perhaps the temperature of the icy ring particles themselves, or subtle resonant interactions with Quaoar's existing moon, might be preventing the material from clumping together the way theory predicts it should. Quaoar is far from the only lesser-known large world hiding in this region, Orcus. Sometimes informally nicknamed the anti-Pluto because its orbit closely mirrors Pluto's own 3:2 resonance with Neptune, while remaining almost perfectly out of step with it, so that when Pluto is closest to the Sun, Orcus tends to be near its farthest point, and the two worlds essentially never come close to one another, despite sharing such similar orbital rhythms. Gong, another sizable dwarf planet candidate, with a distinctly reddish surface and its own small moon named Xiangliu, orbits on a path tilted so steeply relative to the other planets that it stands out as one of the most extreme members of the resonant population. Varda, smaller still but notable for hosting a moon nearly half its own size, adds yet another example to the growing list of binary systems that seem to define this region far more commonly than anywhere else in the solar system. Each of these worlds remains known to us only through faint telescope observations, their surfaces, compositions, and even their exact sizes still carrying meaningful uncertainty, waiting for some future mission or some fortunate stellar occultation to finally reveal the kind of close-up detail that transformed our understanding of Pluto and Aerokoth. Every one of them is a genuine, distinct world, its own history written into its surface chemistry and orbital path, and every one of them remains, for now, little more than a distant point of light and a handful of careful measurements, a reminder of just how much individual character and mystery is still packed into a region most people assume is simply empty space. The reddish tholins found coating so many Kuiper belt surfaces are more than just a visual curiosity, because similar organic compounds are believed to have played a genuine role in the earliest chemistry of life on Earth. Tholins form when relatively simple molecules like methane, ethane, and nitrogen are exposed for extended periods to ultraviolet light and cosmic radiation, gradually breaking apart and reassembling into longer, more complex carbon-based chains, some of which closely resemble the basic molecular building blocks found in amino acids and other compounds essential to biology as we understand it. These are not the same as living material, and no one seriously proposes that tholins themselves are alive in any sense. But they represent a crucial intermediate step, complex prebiotic chemistry occurring naturally, entirely without any biological process at all, driven purely by simple physics and chemistry operating over vast stretches of time in the cold, dark environment of the outer solar system. During the earliest history of Earth, a period when our planet was still being bombarded relatively frequently by comets and other icy debris arriving from the outer solar system, At least some of this same complex organic material would have rained down onto our young planet's surface, delivered by impacts alongside the water ice that many scientists believe helped fill Earth's early oceans in the first place. This has led to a compelling, though still not definitively proven, scientific hypothesis that at least some of the raw organic material necessary for life to eventually emerge on Earth may have arrived from precisely this region, carried inward by comets whose ultimate origin traces back to the same ancient, icy disk that still surrounds our solar system today in the form of the modern Kuiper belt. If this hypothesis holds, it would mean the Kuiper belt is not simply a passive, frozen, leftover from planetary formation, sitting quietly at the edge of our solar system doing nothing of consequence. It would instead represent a genuine, active contributor to the deep chemical history that eventually led to life arising on Earth, an enormous, distant reservoir of exactly the kind of complex, carbon-rich material that early biology needed as its raw ingredients, patiently delivered inward across billions of years through the same chaotic process of gravitational scattering and cometary ejection described earlier. It is a striking thought that the same distant, frozen region capable of hiding an undetected planet-sized world, the same region responsible for genuinely unpredictable, chaotic orbital behavior, and the same region that remains less thoroughly explored than almost anywhere else in our solar system, may also have quietly delivered some of the essential raw material that eventually made our own existence here on Earth possible in the first place. Charon's origin offers one more example of how violent, formative events from billions of years ago continue to shape the Kuiper belt's present-day architecture. The leading model for Charon's formation closely echoes the giant impact hypothesis long proposed for the origin of Earth's own moon, a scenario in which a Mars-sized body struck the young Earth at a glancing angle, ejecting enough molten debris into orbit to eventually coalesce into the moon we see today. For Pluto and Charon, the impacting body is believed to have been roughly similar in size to Pluto itself, striking at just the right angle and speed not to shatter or merge with Pluto entirely, but instead to knock loose an enormous quantity of icy material that gradually gathered together in orbit, forming Charon as a single, large companion rather than a scattered ring or a handful of smaller fragments. This explains why Charon is so unusually large relative to its parent world, with roughly half of Pluto's diameter, a size ratio far more extreme than the ratio between Earth and our own moon, and one that is directly responsible for the unusual shared orbital point the two bodies rotate around rather than a simple planet and satellite relationship. The smaller moons, Styx, Nix, Kerberos, and Hydra, likely formed from the leftover debris scattered during this same ancient collision, material that never fully gathered into Charon itself, but instead settled into stable orbits further out. Exactly the kind of debris field that could later become gravitationally stirred into the chaotic tumbling rotation states we still observe on some of these small moons today. This single ancient impact, then, explains an entire chain of otherwise puzzling observations: Charon's unusually large size, the shared orbital point between the two bodies, the existence and rough composition of the four smaller moons, and even the strange, unpredictable tumbling seen on at least two of them, all tracing back to one violent, formative event that likely occurred within the first few 100 million years after the solar system itself came into being. It is a pattern that repeats throughout the Kuiper belt. Individual violent events, whether the Charon-forming impact, the collision that created Haumea's elongated shape and its collisional family, or the countless smaller impacts that shaped the surfaces of nearly every world in this region, each leaving a permanent, traceable fingerprint that continues shaping the orbits, shapes, and behavior of these worlds billions of years later, in a region cold and calm enough that almost nothing ever fully erases the evidence. Officially, only a small handful of Kuiper belt objects have been formally recognized as dwarf planets by the International Astronomical Union, Pluto, Eris, Haumea, and Makemake among them. Yet many planetary scientists consider this official list to be a significant undercount of how many genuinely round, geologically differentiated worlds actually exist within this region. Based purely on the physical criteria involved, roughly enough mass and internal gravity for a body to pull itself into a round or nearly round shape, researchers have proposed that well over 100 additional Kuiper belt objects likely qualify as dwarf planets in every meaningful physical sense, even though most have never been formally reviewed or officially classified as such. Objects like Quaoar, Orcus, Gonggong, Varda, and Sedna are widely considered dwarf planets by many working scientists in practice, regardless of their official bureaucratic status, simply because their estimated sizes and known physical properties strongly suggest they meet the basic physical requirement of being large enough for their own gravity to have pulled them into a rounded shape. The formal classification process has simply not kept pace with the rate of discovery, partly because confirming a candidate object's shape and size with enough precision to make an official determination often requires exactly the kind of detailed observation, stellar occultations, high-resolution imaging, or direct spacecraft visits, that remains difficult and time-consuming to obtain for objects this distant and this faint. This means the true number of dwarf planets in our solar system, using a purely physical rather than bureaucratic definition, may already exceed 100, with the real total likely climbing well beyond that, as survey telescopes continue finding smaller, fainter candidates deeper into this vast, largely unmapped region. Contrast this with the simple mental model many people still carry: a solar system containing 8 planets and nothing else of comparable individual significance, and the gap between public perception and current scientific understanding becomes clear. Our solar system likely contains not 8 distinct rounded worlds, but well over 100, the overwhelming majority of them orbiting quietly in the Kuiper belt and the neighboring scattered disk, each one a genuine, differentiated, geologically complex world in its own right, and each one still waiting, in most cases, for even a single detailed photograph to confirm exactly what it looks like up close. Every newly discovered Kuiper belt object begins its existence not with a name, but with a provisional designation, a string of numbers and letters that encodes the year and rough timing of its discovery, a temporary label that can remain in place for years, sometimes even decades, before an object earns an official, permanent name. This delay is not bureaucratic laziness. An object cannot receive a permanent name until its orbit has been tracked and confirmed with enough precision to rule out any possibility that it might simply be lost again, drifting back into the vast, undifferentiated darkness from which it was briefly, temporarily glimpsed. Because Kuiper belt objects move so slowly across the sky, a direct consequence of their enormous distance from the Sun, confirming an orbit with sufficient confidence can require repeated observations spread across several years, patiently tracking the same faint point of light across multiple oppositions before its path becomes mathematically certain. Once an orbit is confirmed, the discoverers earn the right to propose an official name, though that name must still follow a specific naming convention established by the International Astronomical Union. Classical Kuiper belt objects are typically named after figures from creation mythology, honoring deities and legendary beings associated with the origins of the world across a wide range of human cultures, which is why names like Makemake, drawn from Rapa Nui tradition, and Gonggong, drawn from Chinese mythology, sit alongside names rooted in entirely different cultural traditions from around the globe. Resonant objects sharing Pluto's particular orbital rhythm are often named after underworld deities, continuing the thematic connection established when Pluto itself was named after the Roman ruler of the underworld in ancient mythology, a fitting theme for objects orbiting in such a cold, distant, and remote region of the solar system. Scattered disk objects frequently draw their names from other mythological traditions entirely, while detached objects like Sedna, named for an Inuit goddess of the sea, often reflect the specific cultural background of the discovery team, or simply continue whatever thematic naming pattern feels most fitting for an object with such an unusual, extreme orbit. Beyond the professional astronomers operating major telescopes, dedicated citizen science projects have also contributed meaningfully to Kuiper Belt discovery efforts, inviting members of the public to review telescope imagery and help flag potential moving objects that automated software might have overlooked. While professional survey telescopes remain responsible for the vast majority of confirmed discoveries, this ongoing collaboration between professional astronomers and interested members of the public reflects something important about this field: that the sheer volume of sky needing to be searched and the enormous number of faint, slowly moving points of light waiting to be identified is large enough that even careful human eyes, offered freely and without formal training, can still occasionally catch something automated systems missed entirely. Even within the seemingly calm classical Kuiper belt, astronomers have identified a subtle but important division that reveals yet another layer of the region's complicated history. Objects in this population split into two distinct groups, commonly called the cold classicals and the hot classicals, a naming convention that has nothing to do with actual surface temperature and everything to do with orbital inclination, how steeply tilted an object's path is relative to the flat plane where the planets orbit. Cold classical objects travel on remarkably flat, nearly circular orbits, closely aligned with the plane of the planets, and they tend to share a distinct set of physical properties: unusually reflective, icy surfaces, a notably high fraction of binary pairs, and sizes that cluster within a narrower range than the rest of the Kuiper Belt population. Hot classical objects, by contrast, travel on more steeply inclined, tilted orbits and tend to display a wider range of sizes, darker average surfaces, and a lower proportion of binary systems compared to their colder, flatter counterparts. This split strongly suggests that these two groups did not form under identical conditions, despite occupying roughly the same region of space today. The leading explanation proposes that cold classical objects formed essentially undisturbed, in place, gently accumulating from the same calm, gentle accretion process that Arakoth itself provided direct evidence for, largely untouched by the later violence of planetary migration. Hot classical objects, meanwhile, are believed to have formed much closer to the Sun originally, in a region disturbed and scattered during Neptune's outward migration, before eventually settling into orbits that happen to overlap with the classical Kuiper Belt region today, despite having a completely different birthplace and formation history. In other words, the classical Kuiper Belt is not one single population sharing one single origin story, but rather two entirely separate populations of objects that happen to currently occupy overlapping regions of space, one representing the quiet, undisturbed leftovers of the original outer disk, and the other representing displaced survivors of the same violent migration event that scattered the more chaotic populations further out. Untangling these two overlapping groups required extremely careful, statistically rigorous analysis of thousands of individual object orbits, sizes, and colors. And it stands as one of the more subtle, but genuinely important discoveries to emerge from decades of patient Kuiper Belt research, A reminder that even regions which initially appear calm and uniform can conceal an intricately layered history once studied with sufficient care and patience. One of Neptune's own moons offers perhaps the most compelling indirect evidence we have that the Kuiper Belt's population was once far more chaotic and far more prone to close encounters with the giant planets than the relatively calm region we observe today. Triton, Neptune's largest moon, orbits backward compared to the direction Neptune itself rotates, an orbital pattern called retrograde motion that essentially never occurs naturally for a moon that formed alongside its parent planet. Moons, forming from the same disk of material that built their host planet, almost always end up orbiting in the same direction that planet spins, simply as a natural consequence of the shared rotation of the material they condensed from. Triton's backward orbit is the strongest possible signal that it did not form alongside Neptune at all, but was instead captured later, most likely a former Kuiper Belt object, similar in size and composition to Pluto, that wandered too close to Neptune at some point in the ancient past and became gravitationally trapped in orbit rather than continuing on its original path through the outer solar system. This capture event would have been dramatic and violent, likely disrupting Neptune's original system of moons entirely, flinging earlier satellites into wildly altered orbits or ejecting them from the system altogether, before Triton eventually settled into the stable, though backward, orbit it maintains today. Triton's surface strongly supports this captured origin story, showing many of the same exotic ices, nitrogen, methane, and carbon monoxide, found across the modern Kuiper Belt, along with active geysers that periodically erupt nitrogen gas and dark material through cracks in its icy surface, driven by a combination of subsurface heating and seasonal warming from the distant sun. If Triton really is a captured Kuiper Belt object, it means at least one former resident of this ancient, icy disk did not remain adrift in the outer darkness, ejected outward or falling inward as a comet, but instead found a strange, permanent second home, locked in a tight, backward orbit around one of the very planets whose gravity originally scattered the Kuiper Belt into its current chaotic and layered configuration. It stands as a quiet, physical reminder of just how interconnected the history of the outer solar system truly is. Neptune's migration shaped the Kuiper Belt, and in turn, the Kuiper Belt itself may have contributed one of Neptune's own largest and most geologically active moons, an object that began its existence as an anonymous icy body drifting through the same dark, distant region we have spent this entire journey exploring. Beyond the reach of any planet's protective magnetic field, Kuiper Belt objects sit fully exposed to a constant, quiet bombardment of cosmic radiation, a slow, relentless process that has been reshaping their surfaces at the molecular level for billions of years. High-energy cosmic rays, particles accelerated to enormous speeds by distant supernovae and other violent events elsewhere in the galaxy, constantly strike the icy surfaces of these distant worlds, breaking apart simple molecular bonds and triggering complex chemical reactions that would never occur under normal, less energetic conditions. This process, often called space weathering, is fundamentally different from the erosion and weathering we are familiar with on Earth, since there is no wind, no rain, and no liquid water to physically wear surfaces down out here. Instead, weathering in the Kuiper Belt happens at the level of individual chemical bonds, gradually darkening and reddening exposed ices over time, as simple molecules are broken down and reassembled into longer, more complex organic compounds, the same tholins responsible for the reddish coloring seen across so many of these distant worlds. This means that surface color and brightness can actually function as a rough indicator of exposure time, freshly exposed ice, perhaps revealed by a recent impact or by cryovolcanic activity welling up from below, tends to appear brighter and whiter, while ancient, long undisturbed surfaces gradually darken and redden as billions of years of accumulated radiation exposure slowly transform their surface chemistry. Because there is so little internal heat, geological activity, or atmospheric erosion to disturb or refresh most Kuiper belt surfaces, this radiation-driven weathering process can proceed essentially uninterrupted for the entire multi-billion-year lifetime of the solar system, creating some of the most chemically processed, complex organic surfaces found anywhere among the solid bodies of our solar system, entirely without any biological involvement at all. Scientists studying returned samples from more accessible small bodies, alongside detailed spectroscopic observations of Kuiper belt surfaces from powerful telescopes, continue working to fully decode exactly what these complex, radiation-altered surface chemistries can reveal about the original composition of the material that built these worlds in the first place, treating each distinct surface color and chemical signature as another small piece of the puzzle in reconstructing the full history of this ancient, distant region. Sedna deserves a closer look on its own, because its discovery in 2003 genuinely broke the existing models of solar system formation. And scientists still have not settled on a fully satisfying explanation for how it ended up where it is. At its closest approach, Sedna already sits farther from the Sun than Pluto ever travels, and at its farthest point, its orbit stretches out to a distance so extreme that Neptune's gravity, the dominant sculpting force throughout the rest of the Kuiper belt and scattered disk, simply cannot reach it at all. This creates a genuine puzzle, because every mechanism astronomers use to explain unusual orbits elsewhere in the outer solar system relies on gravitational interaction with Neptune or one of the other giant planets. And Sedna's orbit keeps it permanently beyond the range where any of the planets we currently know about could have placed it there. Something else must be responsible, and three main hypotheses currently compete for the best explanation. The first proposes that a star passed relatively close to our young solar system billions of years ago, during the early period when the Sun still resided within its birth. Cluster of siblings formed from the same collapsing cloud of gas and dust, close enough for that passing star's gravity to tug distant, loosely bound objects like Sedna onto their current stretched, distant orbits before drifting away again, leaving its gravitational fingerprint permanently imprinted on Sedna's path. The second hypothesis proposes exactly the massive, undiscovered ninth planet discussed earlier, its gravity reaching out even into this extreme distance, gently shaping Sedna's orbit over long periods of time in a way that would also help explain the broader clustering pattern observed among several similarly extreme, detached objects. The third hypothesis proposes something considerably stranger, that Sedna and its handful of similarly distant companions were not originally part of our solar system at all, but were instead captured from another star's system entirely during a close stellar encounter in the Sun's crowded birth cluster, meaning objects like Sedna may be interstellar refugees hiding in plain sight, their true point of origin belonging to a completely different, now long-departed star. Testing between these competing hypotheses requires exactly the kind of expanded survey work already underway, searching for more extreme, detached objects to better map the true extent and shape of this population, since each hypothesis predicts a subtly different pattern in where and how these distant orbits should be distributed. Until that data arrives in sufficient quantity, Sedna remains a solitary, genuinely unexplained anomaly, an object whose very existence hints that the true edge of our solar system's formative history may extend even further and involve even stranger events. than the already dramatic migration and scattering story captured by the Nice model alone. One of the strangest and least publicized mysteries of the Kuiper belt has nothing to do with a single object at all, but with an abrupt, unexplained edge in the structure of the classical belt itself. Astronomers had generally expected the classical Kuiper belt to gradually thin out as distance from the Sun increased, a slow, steady decline in object density the farther you traveled from Neptune's orbit. Similar to how most other structures in the solar system fade gradually rather than stopping abruptly. Instead, observations reveal something far more sudden, informally nicknamed the Kuiper cliff, a surprisingly sharp drop-off in the number of classical objects found beyond a fairly specific distance from the Sun. Within this boundary, the classical belt appears reasonably populated, containing the numerous, relatively calm objects that define this stable population. Just beyond it, the population density falls away far more steeply than any gradual formation process would naturally predict, almost as if something drew a firm line and stopped material from accumulating any farther out, or as if something later arrived and swept the outer region unusually clean. No fully agreed-upon explanation currently exists for this abrupt cutoff. One leading hypothesis suggests that our current surveys simply have not yet detected the fainter, more distant objects that should exist beyond this boundary, meaning the cliff might be an illusion created by the limits of current telescope sensitivity rather than a genuine physical edge. An explanation that future, more powerful sky surveys should be able to test directly within the coming years. A more dramatic hypothesis proposes that a genuine physical mechanism, potentially an undiscovered planet-sized body passing through this region at some point in the solar system's early history, or perhaps the same hypothetical Planet 9 believed responsible for the clustering of extreme, detached orbits, could have gravitationally cleared this outer region of much of its original material, sculpting the sharp edge we observe today, the same way a planet's own orbital path becomes swept clean of debris over time. If this second explanation eventually proves correct, it would mean the outer classical Kuiper belt is not simply fading into emptiness the farther you travel from the Sun, but has instead been actively, deliberately shaped by the gravity of something we have not yet directly observed. A physical boundary carved into the structure of our own solar system by an object whose existence remains, for now, entirely unconfirmed. Resolving whether the Kuiper cliff reflects a genuine gravitational boundary or simply the current limits of our own observational technology stands as one of the more concrete, testable questions that upcoming survey telescopes are specifically designed to help answer. A mystery hiding in plain sight within data we already have, waiting only for enough additional observation to finally reveal which explanation is correct. Step back from any single object, any single mystery, and a larger picture of the Kuiper belt begins to take shape, one that looks very different from the calm, empty border most people still imagine sitting beyond Neptune. This is a region containing more individual worlds than the rest of the solar system combined. The overwhelming majority of them still unnamed, unphotographed, and in many cases undiscovered entirely, hiding within a population that may exceed 100 genuine dwarf planets once every candidate is properly confirmed. It is a region shaped by ancient violence, Neptune's outward migration, scattering material across the entire outer solar system in a burst of chaos that still echoes today in the resonant rhythms, scattered orbits, and detached, extreme paths we continue to observe billions of years later. It is a region that may currently hide an entire undiscovered planet, its gravity gently herding a small population of extreme, distant objects into an alignment too precise for random chance to easily explain. a world several times more massive than our own, that no telescope has yet managed to directly capture in its lens. It is a region responsible for shaping some of the most captivating comets ever to grace our night sky, their icy material sublimating into glowing tails, only after a multi-billion-year journey that began in near total darkness, far beyond where any of the familiar planets orbit. It is a region that, through its distant, wandering cousins, the icy bodies ejected entirely from our solar system to drift silently through interstellar space, may hold clues to a hidden population of unbound worlds that could genuinely outnumber every star visible in our night sky. It is a region that likely delivered water, and quite possibly the complex organic chemistry that made life on Earth possible in the first place, meaning that in some small but genuine sense, part of the raw material that eventually became every living thing on this planet may trace its origin back to this same cold, distant expanse. And it is a region that remains, even now, more than 3 decades after we first confirmed its existence, mapped only in fragments, understood only in outline. Its true total population, its true total mass, and its true full population of hidden dwarf planets, still resting almost entirely beyond our current observational reach. What makes the Kuiper belt genuinely unsettling is not any single monster lurking in the dark, waiting to strike. It is the sheer scale of what we still do not know, sitting quietly at the edge of our own home solar system, closer to us in cosmic terms than almost anywhere else we might look for genuine mystery, and yet still so poorly charted that a body several times the mass of Earth could plausibly be orbiting out there right now, patiently completing an orbit measured in tens of thousands of years, entirely unnoticed by every telescope humanity has ever built. We like to imagine we have a complete picture of our own solar system, 8 planets, a scattering of moons, an asteroid belt, and then the void. The Kuiper belt quietly reveals just how incomplete that picture actually is. An entire hidden layer of worlds, chaos, and unanswered questions sitting in plain sight, waiting patiently in the dark for the next telescope, the next flyby, or the next careful measurement to finally bring it into focus. Imagine, for a moment, actually standing on the surface of one of these distant, icy worlds, rather than simply studying it through the numbers and models scientists rely on from so many billions of kilometers away. The sky above you would not be black in the way spacecraft imagery sometimes suggests, but a deep, star-saturated darkness filled with far more visible stars than anyone on Earth has ever seen with the naked eye. Since there is no atmosphere here to scatter and dim their light, and no nearby glow from any bright, warming sun to wash out the fainter, more distant points of light scattered across the sky. The sun itself would appear as little more than an unusually brilliant star, offering essentially no warmth against your skin, its disk too small and too dim to cast any meaningful shadow across the icy ground beneath your feet. The ground itself, depending on exactly where you stood, might crunch quietly underfoot like frozen sand, a mixture of water ice hardened into something closer to solid rock at these temperatures, layered with patches of nitrogen or methane frost, so cold that they would instantly freeze any exposed material that came near them. Silence would be absolute, not the kind of quiet found in a quiet room on Earth, but a true, complete silence. Since there is no air here to carry sound at all, no wind to rustle, no distant hum of any kind, just an endless, still quiet stretching in every direction. Looking outward, toward where you know Neptune and the rest of the planets orbit far closer to that faint, distant sun, you would see nothing at all marking their presence. No visible planets, no glowing rings, nothing to indicate that an entire, active planetary system lies relatively nearby, at least on the scale of the wider galaxy. And if you somehow lingered here for centuries, patiently watching, you might eventually notice the faintest, slowest drift of your own position relative to the distant stars, the barely perceptible motion of an orbit so large and so slow that a single full circuit could easily outlast the entire recorded history of human civilization several times over. This is the genuine, physical reality hiding behind every diagram, every simulation, and every careful orbital calculation discussed throughout this journey. A real, tangible, silent landscape of ice and rock and endless dark. Sitting quietly at the edge of the same solar system we call home, patiently waiting there since before the sun itself had finished forming, entirely indifferent to whether we ever finish mapping it at all. Not every object that escapes the Kuiper belt makes the full journey inward to become a short-period comet, and a strange, transitional population called the centaurs occupies the messy middle ground of this migration. Orbiting among the giant planets themselves rather than out in the stable, distant reaches of the Kuiper belt, or safely tucked into the inner solar system. Centaurs are former Kuiper belt and scattered disk objects that have been gravitationally nudged inward far enough to cross the orbits of Uranus, Saturn, or Jupiter, yet have not fallen in close enough to the Sun to fully transition into a typical short-period comet, leaving them suspended in a genuinely unstable, temporary orbital state that computer models suggest can only last a few million years at most. A fleeting existence, by the standards of a solar system, billions of years old. Chiron, the first centaur ever discovered, initially confused astronomers upon its detection in the late 1970s, since its orbit did not neatly match either the asteroid belt population or any known comet family, eventually forcing the creation of an entirely new category to describe it once its true, icy composition and unstable, planet-crossing orbit became clear. Chariklo, another well-studied centaur, made headlines when astronomers discovered it possesses its own thin ring system, an almost unbelievable find for an object only a few hundred kilometers across, and one that demonstrated rings are not exclusively reserved for giant planets, but can apparently form and persist even around small, icy bodies under the right gravitational conditions. Centaurs occupy a genuinely precarious dynamical position, their orbits crossing directly through the gravitational territory of the giant planets, meaning close encounters are essentially inevitable given enough time. Encounters that will eventually fling each centaur either further inward toward an eventual transition into a full short-period comet, or back outward, returning it to the scattered disk population it likely escaped from in the first place. This makes centaurs a genuinely valuable natural laboratory for studying the full migration pathway connecting the ancient, undisturbed Kuiper belt to the bright, active comets we occasionally see streaking across our own night sky, a visible, ongoing snapshot of the same slow, chaotic transition process that has been quietly shaping material at the edge of our solar system for billions of years and that continues shaping it today, with every centaur we currently observe representing a brief, temporary stop along a journey that began in the same distant, frozen region this entire episode has been devoted to exploring. Taken together, the classical belt, the resonant population, the scattered disk, the detached sednoids, the wandering centaurs, and the countless ejected objects drifting silently beyond the sun's reach all together form a single, continuous system, one enormous, interconnected reservoir of primordial material still slowly leaking inward, outward, and occasionally entirely out of the solar system, billions of years after its initial, violent reorganization first began. Nothing about this system has ever fully settled into permanent stability, and nothing about it ever will. Not on any timescale short enough for a single civilization to observe from beginning to end. Standing at the edge of a graveyard the size of a solar system, and we end it having barely scratched its surface. One flyby, a handful of confirmed dwarf planets, and a growing list of questions that continues to outpace every answer we manage to find. Somewhere out there, hidden in that same vast darkness, an entire unseen planet may be quietly shepherding the orbits of its distant, icy neighbors. A boundary of unknown scale may be waiting to be redrawn, once our telescopes finally grow powerful enough to see past it. And countless worlds larger than entire mountain ranges continue drifting in total obscurity, patiently orbiting a sun so distant that its light barely reaches them at all. If this journey into the frozen, chaotic edge of our own solar system fascinated you as much as it fascinated us to research, be sure to like this video and subscribe for more journeys into the cosmos. The Kuiper belt reminds us that home is not always fully mapped, and that even within our own solar system, genuine, uncharted mystery can still be found waiting quietly in the dark, closer than we ever imagined.